today I want to place before you more aptly, without taking much time, the essential ingredients that are required as on today to solve our burning problems, particularly in our infrastructure development activities. Let me share my screen. The screen is visible to you, all of you? May I
Yes,
know?
sir. Yes, sir, it is visible.
My voice is audible
Yeah, it is
clearly?
audible, clear, and it is visible. You can start, sir.
Yes. My dear participants, I have just coined this title, which is other than in the brochure. The title that was earlier given to the uh, members, organizing committee members, was Earthquake Disasters and Mitigation. It's a very broad area, so that many things will come into that title. So that what I wanted to narrow down my deliberations of today. So that's why I coined need for developing sustainable earthquake resisting structures. The theme of this FTP program itself is the sustainability in civil engineering. The sustainability is, it is order of the day today in every profession, not only civil engineering, and it is the need of the hour also. There will be sustainable developments that are taking place over a period of time, but it is inadequate, and there are lot more challenges ahead of us to develop much more effective, sustainable technologies, so-called processes, so as to make our world resilient. Basically, my research area includes the liquefaction of soils and dynamic properties, and to certain extent, soil structure interaction studies, with an emphasis on the earthquake site response analysis, which is one of the most required topic of the day for every profession. As you know that when an earthquake trigger in a particular area, some structures may fail, and in the neighborhood of existing structures which have already failed due to this event, some are standing without any damage. Then an element of doubt will arise about the behavior of the structure and the performance of the structure when you compare between the two identities. One failed structure, another one is a stable structure. What is happening here? So that building might have something inherent property that might have resisted the earthquake forces and sustained well. And another building which could not to resist the earthquake forces might have suffered tremendous damage. There could be n number of regions, and it is a complex problem. Ultimately, the solution is also a complex one. That is why in our infrastructure developmental activities, our tendency is to simplify a complex problem into a simple problem, and to obtain a simple solution against a complex solution, because we are unaware of many things and facts. That's why we always find out the shortcuts. In spite of designing the structures, irrespective of the name of the structure, like bridges, buildings, dams, underground tunnels, based on the strictly complying the codal provisions and standards that are established over a period of time, still we observe failure in the structures. Where is the mistake? What went wrong? whether our code books are not justifiable, or we have some flaws or any inadequacies that are existing in the prevailing codes, or what we learned and understood and implemented is not really right. So all these questions will arise to us. Finally, we'll find out some sort of solution, a simple solution for a complex problem, which doesn't solve the purpose. So we always aim at developing sustainable practices and sustainable technologies. That is possible only through understanding from the case studies or the disasters or the failures from the structure, or learning lessons from the structure, and then we have to implement the corrective measures and identify the gaps that are existing right from the analysis point of view to design and then implementation by the time it reaches an end user. So that is where we have to focus more on the sustainable technologies to withstand our damages during in the event of any natural calamity. See, just look at the global economics losses. I have just taken that literature from the source. In fact, during my presentation, I forgot to acknowledge. Now I am acknowledging. I have just collated information, and based on various researchers, the websites, and the information and the lessons gained by my teachers, my fellow colleagues in my institute, and my dear student friends also. So this is the global economic losses from natural disasters. We just have a look at this graph now. The total disaster, the natural disaster may be due to floods, hurricanes, earthquakes, and after effects of earthquakes or tsunamis and fire hazards, all those things. All these things are included in the global economic statistical manner, so that you can observe here right from 2000. I am having data from 2000 to 2020 here. So this is the economic loss in US billion dollars. And as you observe here, the natural disasters and associated economic losses are exponentially growing, with as low as 93 US billion dollars in 2001, attaining a maximum value of 537 in 2011, and followed by here again 475 billion US dollars in 2017, and then again up and down, again up and down. Definitely this graph will be continued, and few more spikes can be observed in the near future also. So much of economic loss the world is facing, and the stakeholders are at great loss. When you take up the worldwide economic impact of historic earthquakes, strictly speaking, the major natural calamities can be grouped into earthquake damages, fire hazards, earthquake hazards, fire hazards, and then hurricanes, floods, etc. Out of these hazards, the major share will go to earthquakes, strictly speaking. So I just referred the Daniel, the statistics data that is projected in 2012, the World Conference of Earthquake Engineering, paper number 2038. You will get more information on this. Please download this paper and access for much more information on this. And he collated the data for the economic losses and the loss of life during the period 1900 to 2012 here. Afterwards, we don't have that. You just have a look at this pie chart. About 61%, 60 to nearly 62% of the damages or economic losses are mainly due to shaking. during earthquake, the ground shaking here. The ground shaking is the one which is considered as the primary effect. And after effects of ground shaking are considered as secondary effects. So leading to the ground shaking, followed by the ground shaking, the after effects are tsunami. The major share goes to 10.3%, and then landslides goes to 5.1%, and then liquefaction associated damage and economic loss of 3.6%, and then fire hazards. Whenever an earthquake trigger, definitely the first the damages that are seen, particularly in case of lifeline facilities, like water supply is completely lost, and their fire will break out. So all these things are happening, okay, during an earthquake here. So in the fire, economic loss is 13.1%, and NATEC, it means natural hazards triggering technological disasters. Please note that natural hazards triggering technological, okay, disasters is around 6.2% here. This statistics speaks only up to 2012. Now already we are in 2020, 22. So a decade, you just extrapolate linearly, or you can exponentially. It could be of the order of 80%. So that 80% of the economic loss is mainly due to ground shaking, and you can check the secondary effects could be around 20 to 25%. So what is the loss of life? I have collected statistics up to 2000. Here I don't have for under 20 years of data, maybe 2 decades. See, you just to see loss of life is about 55% due to earthquakes. Probably this figure could have been more, because now we are in 2022, 2 decades. So that this is exponentially growing here now. So in order to come down or mitigate these earthquake hazards, the only thing is we have to prevent an earthquake by coming, or otherwise we must protect ourselves, okay, from earthquakes. The first one is highly impossible, because you cannot predict and prevent an earthquake to come. But only thing is there must be a proper scientific preparedness to fight against these natural calamity, earthquakes. So there are two kinds of seismic designs. In fact, now what we follow, all the structural engineers, I use the term without specifying structural engineer, waters engineer, or geotechnical engineer, or seismologist. In general, civil engineer. In general, the civil engineer is more worried about, or much involved in the conventional seismic design. But what we need is sustainable seismic design. This is the art of the day. To, to precisely tell you the difference between these two, conventional seismic design and sustainable seismic design is the expected behavior during and after earthquake. In conventional system, it means in the conventional seismic design, the attention is mainly focused on the response of the structure to code level seismic demand, because we are strictly complying to the code, whatever code suggests, and we never want to deviate from the codal provisions, and we never think over and above the code, and we limit there and then itself, and we'll wash off our hand. Whereas the sustainable seismic design is the post-earthquake attributes of the system, which are important as those during an earthquake here. That's very, very important here. So we just concentrate up to the design of the structure based on the codal provisions, then we'll stop thinking over that. But we never concentrate on, or we never take our one study ahead to see what is the post-earthquake behavior of the structure. So that is possible only by if you adopt a sustainable seismic design. Sustainable seismic design is a relatively new field of study. Please note that it is a new field of study that promises improved human welfare and innovative developments in the field of engineering worldwide. So this is an evolving area which is now started slowly in US and some more fast-forward countries. And no doubt, in coming days, the method of design will be always the sustainable seismic design. So if you incorporate the additional requirements in addition to this conventional seismic design process, so then it will become a complete design philosophy. A structure is said to be seismically sustainable if it is able to prevent actual collapse, overcome residual effects, and lend itself well to post-earthquake realignment and repair. This is what I say. This is what the seismically sustainable structure. It means we always classify, as I understand here, more of the structural engineering fraternity. We're all exposed to codal provisions and design philosophy. What the design philosophy of earthquake resistant design says that a structure should not fail even without exhibiting a minor crack, okay, for small, what are called small earthquakes. However, the design philosophy also says that a structure should not collapse under a great earthquake. It means maximum credible earthquake or credible earthquake here. So in spite of designing the structures strictly complying to the design philosophy, we still the failure of structures. Even though if we employ a factor of safety, we are very good in selecting factor of safety. So factor of safety 2, 3, 4, 5. We start from factor of safety right from the loading, start from again factor of safety for material properties. At the same time, the end products of our analysis, like bending moment, shear force, and the deflection on. So you just add up the factor of safety at each stage, it will be as high as say some 5 or 10. In spite of that, we see a lot of damages during the structures, during a particular event of occurrence of an earthquake here. So I cannot call that as a sustainable seismic design because it is not followed the process of sustainable seismic design. So in order to ensure the sustainable seismic design process, we have to identify the gaps that are existing in the code and we have to improve our understanding a bit. That is possible only by continued research and our sincere effort in acquiring knowledge, at the same time disseminating our understanding or through the process of learning. As I mentioned earlier, the majority of the ground damages or earthquake damages are mainly due to what are called the ground shaking, which is nothing but a primary effect. I just a typical example here. You just observe here. Say I have a what is called a ground profile, a cross section, and this is the bedrock profile. And here the rock outcrop, I can say, so that the rock material is seen. The continuity of the rock is extended to the ground level. I can say it is an outcrop rock, and it is the buried under the ground soil is nothing but bedrock. So this is the 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 soil fill or the state of the soil, which is totally unconsolidated material, highly heterogeneous, non-homogeneous, anisotropic material, and highly deformable material when it is compared to all your rigid structures. So when the ground vibrates due to earthquake here, the ground motions are originated at the bedrock and eventually propagate in a vertically upward direction through the overlying unconsolidated or whatever it may be consolidated soil layers. So in the meanwhile, when the vibrations so caused due to earthquakes, when they pass from the bedrock, reach the overlying ground surface through overlying layers, so they get modified in terms of their magnitude and after effects of this, the ground motion, what we say, the horizontal seismic forces are generated at various levels of the structures. Say, for example, this is the foundation. At this stage, I have taken now elevated flyover or a metro, say. It is resting on what is called a pile cap, and here is a pile foundation. It is a rigid structure, okay, reinforced concrete, and embedded in a soft soil. Automatically, the ground vibrations are get modified by the time they reach the ground surface. And the tendency of this earthquake is to cause inertial forces. So these inertial forces always act, okay, in horizontal direction. So these are all inertial forces that are transmitted to the bottom of the structure at some intermediate levels, at ground level, and again at the top here. The magnitude of these seismic forces that are transmitted from the bedrock to the overlying soil get modified, and thus we cannot have the same calculations like if this force is F1, this is F2, and this is F3. F1 equal to F2 equal to F3 is not acceptable. So the magnitudes are different here. Now, greatest question here is what is the magnitude of the force, horizontal force here, dynamic force? What is the horizontal dynamic force? What is the horizontal dynamic force at here? If you could arrive at a fair estimate of these forces and involve these in your regular structural analysis or analysis of this particular structure design, certainly your structure will be safe and then it is sustainable. But many a times it never happens like that because till today we don't know the exact magnitudes of these horizontal loads that are transmitted to the structure through the overlying medium, and that's why we are erring on the wrong side to really work out what exactly the order of magnitudes of the lateral loads coming on the structure due to earthquakes. So when there is a slight what is called error here, this error will multiply many times and ultimately it lead to unfavorable performance of the structure here. So whenever the underlying motions through the bedrock, when they travel through the overlying soil medium, they get modified in various terms, and that modification is what is called site amplification, okay, or resonance condition. So what is that? During earthquakes, the ground motion parameters such as amplitude of motion, frequency content, and the duration of strong ground motion change as the seismic waves propagate through overlying soil and reaches the ground surface. So this modification in the ground motion parameters is termed as site amplification or soil amplification in geotechnical earthquake engineering. Many code books, they also advise engineers while they are designing the structure for various type structure resting on different kind of soil, what is called an amplification factor. But those values, again, they must be cross-examined, okay, for their validity. That's more important here because the amplification factors, okay, vary widely depending upon the complexity of the soil and then complex ground motions here. So what will happen when an earthquake triggers here? So if earthquake is having certain acceleration, when the motions carried forward from the bedrock to the overlying so through soil layers and reach the ground surface, the acceleration get modified and the frequency content of the ground motion will vary. At the same time, the duration of the ground shaking will also vary here. So this is what is known as an site amplification process, and this is much more attention has to be paid towards this if we are in a position to quantify. And we are all talking about qualitatively. The qualitative estimation does not serve the purpose, and we have to go for quantitative estimation of site amplification and the associated what is called phenomena, a resonance condition here. So now amplification factor I can define for benefit of others. It is the ratio of surface motion to bedrock motion. Please note that suppose when an earthquake travels far off distance and incident at one particular location, it will have say acceleration x. When these acceleration pass through overlying layers, reach the ground surface, the acceleration get modified here. Sometimes it will be modified or it will be remain same. Sometimes it will be manifold. Suppose if it is acceleration amplitude is x here it is some 2 times x, 3 times x here. So you just say surface motion, then nothing but acceleration or velocity or displacement, whatever may be the identified term, and the bedrock motion, this ratio you will get, okay, what is known as amplification factor. This amplification factor is very, very important in the earthquake resistant design of structures. More precise estimation depends on several factors. Till today, we are not having such a well-established technology to arrive at the exact value of amplification factor, but still we do our best to meet this requirement. The one thing, as I mentioned here, the response of the structure, either it is a building, bridge, or dam, whatever may be, ultimately it has to be constructed in soil, okay, to over the foundation. So that any structure will have a superstructure, a foundation, and also the foundation is resting on subsoil. So that the response of the structure always depends upon the superstructure, depends upon the response of the foundation, and the response of the foundation depends upon the response of the soil due to vibrations during an earthquake. A study that is coined, which will take into effect the response of the soil and the response of the foundation and the response of the structure in total as one study, we can call it as soil structure interaction. Invariably, we isolate the building with the foundation as well as soil and do our analysis in a very most conventional manner separately without accounting for the effect of subsoil on the foundation and the effect of the foundation on the structure. We do our analysis and design. Certainly, here there are mismatch in our conventional seismic design, and ultimately we are not focusing on the sustainable seismic design here because the role of subsoil will have tremendous influence on the response or the behavior of the foundation and in turn the behavior on the superstructure here. So we can always say that the subsoil has got a significant or a major role on the seismic resistance of structure and their behavior during the event of any earthquake here. As I mentioned here, I will take up a simple example. Suppose you see the same structure I have taken here. One idealized situation. I have a soft soil here and the depth of overburden. Any soil material that is above, located above bedrock is what is called depth of overburden, say H. And one case, in one situation, I'm having subsoil, and in another situation, I have probably hard or very dense strata. And no doubt these acceleration pass through the overlying medium, reach the ground surface. And definitely here, as these inertial forces are generated onto the ground, the inertial forces are developed here. Say for example, F equal to ma. Even though your mass of the structure is same, but acceleration get modifies here at the top, and the seismic force is different here. At the same time, the same F equal to ma, and as these accelerations get modified through the overlying dense material, the acceleration is different here, acceleration is different here, but the force F here, F is not identical, it will be different here. So that we have altogether a different seismic force at the base of the foundation, and eventually this will cause the vibration of the structure and undesirable displacements or deformations in the structure here. So what we have to understand from this here, without neglecting the role of the subsoil, okay, the influence of the subsoil on the structure must also be studied so that there must be a proper coupling between the superstructure, foundation, and the soil as one unit, and it should be viewed as one particular unit during occurrence of any seismic activity in a particular region. Somebody may ask now, our code book doesn't say any soil structure interaction. Soil structure interaction studies are relatively new field. Now only it is emerging and it is in the research stage. Already most of the code books across the world have implemented this. Even our Indian code also considered the soil structure interaction effect in another manner, not considering as one integral unit like a structure, foundation, and then soil as one entity, but indirectly we are accounting for them. I hope it is not sufficient. But still, in spite of knowing this reality, okay, any structure resting on the soil must be viewed as one integrated structure, and our detailed analysis and design is required. Still, we are neglecting that process. And it is always right to neglect the soil structure interaction. Under what circumstances? When your structure is lightly loaded and it is resting on relatively hard or stiff ground, such as low-rise buildings only. Earlier, there were code of provisions where you can simply construct the buildings to the required number of stories, okay, without considering soil structure interaction effect. Now, there are mandatory requirements from the codal provision that if you are crossing two-story, suppose three-story building, and beyond that, you must compulsorily adopt the soil structure interaction analysis, and you must take the influence of soil on the foundation and the influence of foundation on the structure. Now it is becoming a mandatory, and in most of the curriculum at undergraduate level or particularly postgraduate level at research level, the subject matter has been already coined. See, in this case, I just take up an example. Zenk in 1996, you refer this way. He developed a simple concept by writing a finite element code to identify what is the effect of the overburdened soil on the frequency response of the ground. You just he plotted. See, I have taken here one a ground. Say depth of overburden is say h, and then I want to find out what is the force here, and I don't know what is the frequency of vibration of this particular ground, because the natural frequency of the ground depends upon various factors like stiffness and then mass of the material. So he carried out one study, a case study, and developed a code, and he examined for the distribution of fundamental frequency with the thickness of the soil layer. It means overburden now. Here, sometimes you may get shallow depth, you may find bedrock, a hard stratum, competent stratum, what we say in geotechnical engineering, at very shallow depth, probably 2 meter, 4 meter, 5 meter. In some situations, you may go even beyond 30 meter. You may not get a competent strata like dense soil, but you are getting a soft soil. Now, what is the order of damage that is involved? Definitely, it is directly proportional to the depth of overburden, okay, from the bedrock or above the bedrock to the ground surface. So the fundamental frequency of the ground is very, very important in your soil structure interaction analysis. But we are having so much of expertise in finding natural frequency of our superstructure by means of structural dynamics, but that cannot be used in straightforward way to determine fundamental frequency of or natural frequency of the ground. A homogeneous ground means homogeneous or even layered ground. So he put an effort in 1996, and he just examined for various thickness of the soil, say so many meters, and he plotted natural frequency, and he considered horizontal acceleration coefficient 30% of g. It means acceleration due to gravity is say about 9.81 meter per second square. Approximately it is uh, zero point 0.3 g, or the 3 meter per second square acceleration. And he considered arbitrarily one soil strata having a void ratio 0.75 and coefficient of earth pressure coefficient of pressure at rest condition 0.45, and angle of friction 33 degrees of the soil. These are all properties of the soil, and gamma is unit weight 15 kilonewton per meter cube. And he carried out seismic analysis for varying this particular depth, say 1 meter depth, and again 2 meter, 4 meter, 6 up to 8, 10 meter depth he considered. And he just found out what is the natural frequency of vibration of the ground alone without the structure. Please note that without the structure here, because my objective here is to explain what is the natural frequency of the ground. So as you observe from this figure, it's very clear that as the thickness of the overburden reduces, it will have very high frequencies. For example, at about 2 meter depth of overburden only, the order of frequency is around 9 hertz, very high frequency component. Suppose if the depth of overburden increases abruptly, say for example 10 meter, your frequency is around 3 hertz here. Please note that around 3 hertz. Even if you increase, go beyond 10 meter, 20 meter, 30 meter, the frequency value still come down, so that it will have a lower frequency component. So that a lower frequency component, as you all know from structural dynamics, will have long oscillations, a long period of vibrations, and so that what will happen, you will find out large displacements in the structures for which we are not in a position to design for large deformations, and we will always limit our deformations. So another thing, he correlated in another way. Suppose if it is same uh, 10 meter depth of overburden for the same soil properties, he varied accelerations coefficient. Say 30% of acceleration, that is 0.3 g he considered, and he found out this value. And suppose if the level of acceleration, vibrations, or amplitude of vibration is smaller, then what will happen? So 0.1 g is around 4.5 hertz, and then 0.2 g 4 hertz, and zero point 0.3 g, as we observed here, it is 3 hertz. And at the same time, suppose 0.4 g, it's almost zero point 0.5 fundamental frequency. What you can conclude from this investigation is a very useful information for a design engineer, that okay, higher the acceleration for the same column, you will get the lower frequency. At the same time, increase the depth of overburden, you are having very low frequency, which is not conducive to the structures, and this must be taken into care while designing our structures here. This will throw a lot of information for us, though it seems to be a basic requirement. So I will just want to take you to glimpse of photographs through some damages during previous earthquakes. The more, the most classical earthquake in our India, 2001, supposed to be, it is an eye opener in our India, because this was one of the biggest earthquake ever seen in India, that occurred on 26 January 2001, early morning 8:46. It's a special day, 26, as you all know that. And the depth of the earthquake was around 24.8 kilometer, approximately 25 kilometer, and the magnitude of earthquake was 7.7, a great earthquake. India never had this earthquake. Of course, before 1950s, some earthquake and all, okay, but not that much damages were observed here. So this earthquake triggered in in Gujarat state, at a place called Bhuj. It's a small town in Gujarat. Hence, it is called Bhuj earthquake. So this is the epicenter of the earthquake, and this epicenter was nearly around 260 kilometers from Ahmedabad. So Ahmedabad here, and here it is a Gandhinagar, and here is Ahmedabad. What is the speciality? Why I'm highlighting here Ahmedabad? Because though earthquake occurred at a distance of 260 kilometers in Bhuj town, there is propagation of the waves, propagation of the vibrations from the epicenter location over a distance of 260 kilometers, traveled to Ahmedabad and caused tremendous damage by means of site effects. So that's why I'm telling you, the site amplification and site effect is a very, very important, okay, in earthquake resistant design of structures. Though earthquake occurred in this particular region, we noticed, we experienced so much of damage at a far off distance, nearly about 260 kilometers. So for the benefit of those who are new to this earthquake engineering terminology, I just throw light on this. Okay, I told you epicenter. Please note that there is a misnomer that epicenter is below the ground level. It's not like that. Okay, it is a point. Epicenter is a point on the ground surface, and here is a point what is called focus, where exactly the earthquake triggers because of one portion of the rock mass slides here. We call it as rock fault rupture. So here huge strain energy that is stored when in its equilibrium condition, so there is some amount of disturbance. so that the rock fault, okay, rupture takes place and huge sound waves are generated. These sound waves are converted into mechanical waves, and they will eventually travel in all possible direction and reach the ground surface. The point where exactly the fault rupture takes place, release of energy, stored energy, is called what is called focus, and a point vertically projected onto the ground surface is what is called epicenter. And the vertical distance between the epicenter, a point on the ground surface, to the point focus beneath the ground surface is what is called the focal depth. That's the depth of earthquake. Sometimes people in the media say immediately, such a magnitude of earthquake triggered or occurred at a depth of this one. This is always focal depth is 1.25. I would like to tell you here, as the depth of the focal depth decreases, the damage potential is exponential. So greater the focal depth, lesser is the damage. So this is one of the predominant factor that greatly decide the potential of damage during any earthquake. This is the damage pattern in Ahmedabad city. See, this is a part of a map, part of portion of the map of Ahmedabad. You know that Ahmedabad, in Ahmedabad, here is the Sabarmati River, which flows from north to south here. Okay. Earlier, that area was completely occupied and thickly populated towards east of here. Here is the east, and here is the west zone. Here, this area was completely occupied, and it was built over a period of time. And this area is relatively new area, where huge infrastructure developments were taking place during that particular time, and many buildings have come up, and many structures were put up in this building in the new area. So here, what is the speciality of this? So this plot, this map I have taken from Bandari and Sharma, a scientist from CBRI, who visited the site immediately after the earthquake, and documented the damages, the kind of damages, and the number of buildings, and also documented the number of deaths also. They plotted all these. So they have mentioned here, these are all collapsed buildings, and this is the cluster area. Wherever you see dots, they're all cluster of area, nearly about 1 kilometer radius here. Then so many buildings located in this cluster of area, and these three bands, 1, 2, 3 bands, okay, has suffered tremendous damage of buildings here in this region. What is the reason for that? So we conducted one case study on this. I would like to present that case study and what was the reason for the failure of buildings in this particular area. And it was astonishing factor to see that no damage was seen in the right of this particular area, particularly old region, where already the developments have taken place here. And this almost coined a what is called, this was a new area where infrastructure developments are put up very recently, well before occurrence of earthquake. So minor damages in buildings up to 3 stories were observed in this cluster area, and several buildings with 4 floors and then 10 floors totally or partially collapsed. See here, thick alluvial soil deposit underlies the city of Ahmedabad here. Even if you go beyond to 10 meter, 15 meter, you will find out unconsolidated sandy soil, okay, on the banks of river Sabarmati here. So this area was more vulnerable, and we never thought of such a tremendous damage in this particular area, because the proper site amplification was not quantified during that time. And we wanted to take up a study here, and we collected the data from available sources, and we used our uh, analysis by using that data, and we came with a conclusion for the tremendous damage of the G+4 building and then G+10 building only. And the many deaths, they also documented more than 700 people, as the report speaks. So these are all typical damages to buildings. This is one apartment building, G+8 story, and this is G+4 story, and this is G+3 story building in that particular area, in the right bank of Sabarmati River. See, these are all some of the buildings damages in during Northridge earthquake 1994. Have you designed your columns for this kind of failure? Please note that we always treat that column as a compression member, and we'll just find out what is called bending moment, and we'll design the columns, and then if at all if there's shear, then we'll shear. So there is one point, some literature says that this kind of failure was attributed to large vertical vibrations. So this deserves some further study by conducting some experiments or some numerical model. The kind of damage that associated during Northeast earthquake due to ground shaking only. I'm talking about ground shaking. This is another building. You just see here, these buildings, okay, they are safe to certain extent. Only these buildings collapsed here. So these are some of the damages to National Highway number 8 in Gujarat due to ground shaking only. Use the order of these cracks were order of about 50 centimeter to 60 centimeter and as deep as 1 to 1.5 meter. Longitudinal cracks to several kilometers. And in fact, what I came to know that it's a newly built road, and this is one toll booth at the entrance of this particular highway. And this is one of the classical example where very recent earthquake in Japan on 11th March 2011 occurred at 2:30 p.m. with a magnitude of 9. This is one of the greatest earthquake Japanese ever seen, and they have a technology. They have a technology to design and withstand the structure up to 7.5 magnitude earthquake, even 8 magnitude earthquake, and they never expected this kind of or this order of earthquake, and which resulted tsunami also. And this was one of the new road that was built actually. This suffered huge damage. This is in Kobe earthquake in 17th January 1995, a great earthquake. You just see that it's an express flyover, simply toppled. Okay, and here is a landslide, deep landslide during the same earthquake. This is one of the magnificent landslide Taiwan during Taiwan earthquake 1999 here. These things I have collected from the previous literature just to highlight the importance of ground shaking during an earthquake. See, one thing we have to see that, as you all know that, and it is understood well that the subsoil has great role on the response of the structure or the behavior of the structure. Definitely, one can estimate the risk rate. That's very, very important here. But nobody is making an attempt to quantify the risk rate of subsoil on structures. Japanese were the first people to, before advent of these modern technology developments or modern instruments, seismic instruments and their measurements, very based on very thumb rule, based on the site visits, based on the deaths and the number of buildings collapsed in the region, uh, on very conventional manner, they arrived at one term, what is called the damage potential. It means the potential of damage to built environment was assessed in terms of damage index by Japanese in the year between 1920 and then 23, because not much techniques were available to quantify the damage potential of buildings then. So they developed simple formula by statistical analysis, a simple expression 13 times exponent 0.0038 times delta. But delta is nothing but epicentral distance in kilometer. As I mentioned, what is the epicentral distance here? So this is the epicenter of the earthquake, and this is a place of recording. Suppose if you have an instrument located at some region which can record the vibrations. So the distance from the epicenter and then place of interest of recording an earthquake is what's called epicentral distance. At the same time, closer the epicenter for this instrument, definitely high intensity earthquakes are recorded. And as you keep moving away from the epicenter, the intensity of the earthquake gradually decreases here. So that's what it's clearly highlighted here. This distance increases, it is exponentially decreasing here damage potential. So this what I explained already, the focus epicenter, and based on this expression, they documented some of the failures, particularly in reinforced concretes, on classifying the ground on which the buildings were resting. So one is a soft ground, very ad hoc manner they coined this term, soft ground, but there is no exact definition for soft ground, and we have to visualize these terms, okay, scientifically in a very fruitful geotechnical manner. And is the hard ground. They are plotted on x-axis number of stories, y-axis damage index by this formula. This is for only reinforced concrete, and they took the data from failures of buildings during San Francisco earthquake in 1906 in America, and they explained. Observe this trend now. So since the soft ground, as you increase the height of the structure, the damage potential or damage index is exponentially growing. What you can understand from, if the subsoil is poor soil, soft soil, and if you build a reinforced concrete structures, definitely it will have significant effect on the performance of the structure. On the other hand, if it is hard ground, no doubt the damage potential is increasing to certain extent. Afterwards, okay, it is decreasing. Here it is required some sort of research or further studies were required, and it was stopped at that particular time itself. In contrast to these reinforced concrete buildings, they also documented the earthquake damage to masonry buildings, either stone masonry or brick masonry, whatever it may be. They used the same formula. They took the data from two earthquakes: Grand Kanto earthquake in Japan 93, no, 23, Long Beach earthquake in 1993, Japan only. Please make an observation on x and y axis: number of stories, damage index, number of stories, damage index. You just see here in two cases, as the number of story decreases on soft ground, the damage potential decreases. Again, soft ground gradually increase, again suddenly decrease. Hard ground, it is increasing here. So similarly here, what you can notice from here, soft ground, the damage potential decreases, hard ground, it is increases. What you can conclude from these two comparisons, our understanding is that the brick masonry buildings survive better on soft ground, but however, they do not perform better on hard ground. In other words, the reinforced concrete buildings, they are more vulnerable when they are constructed in soft ground. Here is the thing where exactly we have to do soil structure interaction analysis, and utmost measures must be taken to consider the effect of subsoil on reinforced concrete building performance. So for effective, now these are all the damage patterns and many terms that are associated with the damage potential, like site amplification for all those things. But one of the prime importance for earthquake disaster mitigation is order of the day site specific ground response studies. That is very, very important. If you have this site specific ground response analysis or studies in a particular area, then only it is possible for us to develop effective earthquake disaster mitigation strategies. What is this site specific ground response study or ground response analysis studies? So these studies allow engineers to calculate the natural periods of time, natural period of vibration or frequency of vibration during design earthquakes, assess ground motion amplification. This is very, very important here. As I mentioned, by what times the acceleration get modified from the bedrock to the ground surface, how many folds, and provide these studies will provide useful information for structural engineers with various parameters such as response spectra for design and then safety evaluation of structures, particularly for performance level of structures here. So it's a very, very important aspect. Once one must look into this. At the same time, evaluate the potential for liquefaction of soil. I will little bit come to this topic later because the major damages that are attributed to liquefaction are plenty during vibrations. Conduct first analytical phase of seismic stability evaluations for dams, slopes, and embankment. They're all more vulnerable and highly sensitive to ground vibrations, and definitely the predominant factors that control the performance of these lifeline structures must also be evaluated. That is possible only by conducting site-specific ground response studies in a particular region. Now, I would like to throw some light on the one of the case studies. Please note that due to constraint of the time, as the organizers have given me only 1.5 hour time, if I want to present all the case studies in detail, it may require more than one case study may require more than 1 hour for me. So I always suggest the participants to refer this journal. Whatever I am presenting now here, I just provide you glimpses of the uh, what we presented case study, a detailed report in the Journal of Current Science in volume 87, number 10, November 2004. You can download or get it from the Current Science Journal. This is authored by myself and then Ramana and Armantrao for IIT Delhi, and Professor Sitaram, my teacher, my guru. Right now he is the director IIT Guwahati. So we wanted to explore what is the reason for the damages to buildings in Ahmedabad during 2001 Bhuj earthquake. Soon after the earthquake, all research community, right from all IITs and primary other institutions, even some experts and then researcher from abroad visited the site and then conducted postmortem studies of these buildings, including the bridges, dams, okay, in the entire state of the Gujarat. And then finally, they submitted one report to the government. At the same time, all these damages are documented in one report, concise report in Earthquake Research Engineering Institute, and I will give that reference also. You can access that information, and you can get more knowledge or more information for your further mm, analysis. Now, these are, as I mentioned already, these are the damages that the buildings suffered during that particular earthquake. G plus 8 story building, 4 story, and 3 story. And we wanted to explore what is the reason for this kind of failure for the buildings. So here is the Bhuj, and here is the Ahmedabad. It's around 260 kilometers from the area distance. So this, fortunately, unfortunately, no recording instruments were available close to the epicenter, and fortunately, there is one post and customs office tower in Ahmedabad. So it is a 10-story building. In all the stories, they have housed strong ground motion recording devices, and this is the ground motion that is recorded at the ground floor of the building, in the building, passport office building, and we use this time history of acceleration at the ground level to conduct our further analysis. We just make a close observation here. This is the Bhuj earthquake record. These accelerations are in G, and here it is time in seconds. So this is around 0.11 G, approximately 1.1 meter per second square. In fact, during earthquake at the epicenter, we back calculated the acceleration was 3.3 meter per second square. By the time wave propagated, or these seismic waves traveled from the epicenter to the place of recording, nearly 260 kilometer, the amplitude got decreased, and at the Ahmedabad site it was around 1.1 meter per second square, and we converted this into FFT to observe the frequency content distribution. Please note that the only one amplitude and one frequency is not important to conduct a site-specific earthquake response study. It's always important the amplitude of vibration as well as the frequency content. At the same time, the duration of the strong ground motion is a very important factors which decide upon the potentiality of the damages in structures. See here we converted this time history of acceleration into frequency response manner. So this is the amplitude, and we identified several peak frequencies, say 1, 2, 3, and then 4. These were the resulting frequencies from the earthquakes, spikes, and the predominant frequencies. So it's around as low as 0.85 or 86, and this is around 1.172. Third is around 1 point approximately 2. Fourth is this. This is the frequency content. Please note that it is not the one frequency we have to consider while doing our analysis. It is the frequency content is important. And so these are the range of frequencies that lie between zero point 0.8 hertz or 0.9 hertz to 3.32 hertz. Now, this is the geotechnical information data. So we collected the data, geotechnical information data by means of a borehole in that particular location where exactly the buildings collapsed. Here you can see the depth up to, we have gone up to 15-meter depth. And here the standard penetration test results are prevailing here. 7, 10, 11, 17, and up to say 6 to 7 meter, 7.5 meter, it is almost a loose state. And afterwards 17 to again 32 medium dense state. So here upper portions, they constitute relatively unconsolidated sediments. Now, conduct, in order to find out the natural frequency of the ground here, because when the wave propagate from the deepest point, by the time they reach the ground surface, the frequency content get modified here. So that we wanted to know what is the natural frequency of this particular ground. Okay, so we carried out this analysis by using one-dimensional wave propagation analysis by employing the software Shake 2000, and the method of analysis is equivalent linear analysis. Similar other softwares are available like Deep Soil. So you can also conduct analysis either in linear or non-linear analysis. Now, after conducting the analysis, we wanted to find out what is the natural frequency of the ground. So this is the amplification ratio, and this is the frequency distribution. You just see here, once you use this shared program, it will give you the distribution of amplification with range of frequencies here. You can notice maximum amplification of ground motion parameters, okay, at a frequency of around 3.51 hertz. Yeah, almost 3.51 hertz. So this was the natural frequency of the ground in Ahmedabad city here. Here, this region, okay, the natural period of vibration or natural frequency was around 3.51 hertz frequency. So here, we again cross-checked with Zeng, okay, what exactly, whether our analysis is correct or not. Please note that here it is approximately 0.11 G. So the depth of the soil is 10 meter, but we took around 15-meter depth. So here, if you want to make an approximation 0.11, somewhere here we are getting nearly 4. Please note that nearly 4 value, nearly 4 or 4.2 value. But if you just go slightly beyond here, so we are getting almost close to 3.51. So nearly 4, 4.51, okay, are almost matching with each other as proposed by Jen. Now our objective was to determine or to find out the natural frequency of these buildings, 4 to 10-story buildings. So here one limitation we had in our study, we never conducted modeling of the soil, foundation, and structure, and we conducted very simplified analysis. Separate analysis we have considered for the buildings as well as the soil deposit, so that we wanted to verify whether the natural frequency of the ground and the natural frequency of these 4 to 10-story buildings are matching or near equal or not, so that when the resulting frequencies, okay, from the ground and the natural frequency of the building, they are each other, close to each other, a kind of what is called resonance we can expect, okay, in the situation. So when the structures are subjected to resonance, we can expect large oscillations and then maximum damage by means of resonance. So now we wanted to find out what is the fundamental period of vibration of the building, TL. This is a schematic diagram I have taken from the report submitted by CVR Murthy and others, a report for disaster management, Gujarat Disaster Management Authority, Gujarat. A simple one page I have taken here. So here is a 10-story building, and here it is, say that symmetric building, and here they conducted what is called the model analysis, and you just find out what is the frequency of vibration here. So as the vibration is continued, the amplitude of motion or oscillation increases and again comes down here. So this we can consider it as a maximum response. And this is the diagram which can exhibit. It is a 2-story, and this is 5-story building, 10-story, and then 25-story. So as the height of the story increases here, so automatically the number of story increases, the frequency, the natural period of vibration will also increase. It means the frequency will decrease here. So on the same lines, we carried out uh, determination of natural frequency by using uh, finite element modeling by using SAP software. Considered 1 bay 1 story, 1 bay 2 story, and then 1 bay 3 story, 1 bay up to 10 story, and 2 bay 1 story, 2 bay 2, and then 2 bay 10 story. Similarly, 3 bay up to 10 story, 4 bay up to 10 story, and we plotted these frequency response curves with respect to story height. See here, this is 2 story, 3, 4, 5, 6 up to 10 story, and the frequency here. And our interest was the frequency content distribution, what we got from the Bhuj earthquake. Here it is 0.86, 1.12. So it is 1 hertz to around nearly 4 hertz, say 3.5 or 4 hertz. So you just make a close observation here. So our majority of the damages, tremendous damages to built environment for only 4-story and then 10-story building. Say it is 4-story means it's approximately it is 3 hertz, and then 1 story here it is 10-story means it's approximately 1 hertz. So these frequency range are in the narrow band, okay, with the frequency of 4 to 10-story building, and we made a comparison here. Comparison of frequencies. Frequency content of earthquake recorded at Ahmedabad 0.86 to 3.32 hertz. Natural frequency, what we found, okay, from the Shake analysis, Shake program, it's 3.51 hertz. And natural frequency of 4 to 10-story building, we have find between in this particular range. See all these frequencies here, 0.8 hertz, it's 1 hertz close to each other, 3.2, 3.51, 3, and are all almost okay, close to each other. So observation and our understanding from the study, based on that, we drawn our conclusion that the high degree of damage to multi-story buildings was essentially due to transfer of large accelerations to high-rise buildings by site amplification or soil amplification. Further, close matching of the resulting wave frequencies with the resonant frequencies of high-rise structures is an added factor for their collapse. What we observed here, the ground motions got amplified, the frequency content, this was the ground frequency, and this is the earthquake frequency. In this particular range, they are close to each other and causing what is called the resonance in the structure. And this resonance led to the damage to such 4 to 10-story buildings. Now, another case study uh, we have carried out. This is site-specific earthquake response study for hazard assessment in Kolkata city, India. Nowadays, the priority has been given for microzonation of cities, particularly mega cities. Started with mega cities like microzonation of Delhi, microzonation of Mumbai city, microzonation of Chennai city, microzonation of Bangalore city, It has been done. Delhi micronization studies were carried by IIT Delhi. Bangalore micronization studies were carried out by Indian Institute of Science by Professor T.C. Sitaram. Like that, major cities were undertaken for micronization studies for hazard assessment. So only after this Bhuj earthquake, which is one of the eye opener. So on the similar lines, okay, micronization of Calcutta city was to take up, and as a preliminary study, we had an opportunity to look into some site conditions, and we wanted to develop amplification maps, okay, in for Calcutta region. This study was jointly conducted by me as well as my professor Subhamay Bhattacharya is faculty in Oxford University, Department of Engineering Science, Oxford University, UK. Now he is a professor and chair in University of Surrey presently. And this our the total understanding and then report has been presented in this International Journal of Natural Hazards. It's the International Journal of International Society for Prevention and Mitigation of Natural Hazards. You can access this. Okay, you can download this, and it is around 36 pages of paper that is presented in this particular journal. Now, without taking much of the time, I will just go back and then explain the need for conducting site-specific earthquake response study in Kolkata city. So these are all significant earthquakes in West Bengal, right from 1764. See here, the major earthquakes that occurred in Bihar in 1842 felt at Kolkata and was observed in North Bay of Bengal. And I listed in the West Bengal the major and significant earthquakes over a period of time. From the database, please note that this is the database from where I collected for the significant earthquakes. So here, one more earthquake in 1897, Assam Meghalaya earthquake, magnitude 8.1, back calculated, and most powerful intraplate earthquake in the Indian subcontinent, damage with a intensity scale 7 in Kolkata area. At the same time, in January 1934, magnitude 8 tremors were felt strongly at many places in West Bengal, including Calcutta. Then 1935, surface wave magnitude, prolonged tremors were felt at Kolkata. And 1950, 8.6 magnitude, the most powerful earthquake in South Asia. Earthquake caused damage to buildings in Kolkata. And 1964, 5.2, maximum intensity in Kolkata with the intensity scale of 5 here. So this information created our interest to conduct some site response studies and to find out ground amplification factor, which will serve as a tool for or an input for seismic hazard analysis of Kolkata city as well as seismic microzonation of Kolkata city. And of course, this study was supported for me by National Program on Earthquake Engineering, Ministry of Human Resources and Development, and it is my postdoctoral work during 2007 when I was in Oxford, okay, UK. So we wanted to concentrate on a particular location where the infrastructures yet to come. It means Salt Lake City. This is a completely reclaimed land. This is Razarat city reclaimed land here, and here it is EIIMS. So this is EMS is close to river Ganges, one locality, and another Howrah area here, and this Hooghly River runs okay from here north to south and joins Bay of Bengal here. So this is a proposed area where the new infrastructure facilities have to be established on both left bank as well as the right bank of the Hooghly River. So here the geotechnical information that is required for site response analysis we collected from the municipal agencies of Calcutta and other uh, builders, and we took soil samples from all these area and we classified and then grouped them into 4 category: category 1, category 2, category 3, category 4. It means We named them as type 1, type 2, type 3, and then type 4. Now, these are all the soil conditions. You just observe here, we never find rock. Even if you go up to 60-meter depth, we cannot get rock. It is only clay. Here it is silty, soft clay. And then this is bluish gray silt clay, dense yellow fine silt, and then stiff brownish case silt, and very dense fine sand. Only sand and silt mixtures, okay, existing for a great depth. As I mentioned earlier, the depth of overburden plays a dominant role, okay, on the ground response studies, and definitely the damage potential is exponential. And another site we got data up to 36-meter. Here also no rock, silty clay, loose brownish shanty sand. At the same time, the third one also went up to 41-meter. No way we found rock. Only thing is silty soil was found. Another location, 30-meter depth, and you can see that is up to here fill and here low plasticity clay, silt, and then here also intermediate plasticity clay and silt. Here it is silty sand to a certain extent, and all are unconsolidated in state. And we wanted to have the standard penetration test data or stiffness of the soil in all these locations. And we collected this data. These are all standard penetration test values. And we want for our analysis what is known as the shear wave velocity. Shear wave velocity has to be measured in the site. Nowadays, facilities are available to measure the shear wave velocities right from the ground surface to an extent of 100-meter, sometimes even 200-meter. But as that facility was not available during the time, we back calculated from the available standard penetration test values. There is a correlation that exists between standard penetration test value as well as the shear wave velocity. We use Japan Road Association. Japan Road Association, you just take Japan Road Association. It has highlighted the methodology or procedure to calculate the shear wave velocities in the absence of the data, measured data with respect to standard penetration test values. And here, in order to conduct ground response studies, the one important thing that was missing here, no recorded ground motion, at least while analyzing for the case study with the Bhuj earthquake, we had recorded accelerations, but here no recorded ground motion was available. And we have to develop what are called synthetic acceleration. Please note that this is relatively a new area where without waiting for an earthquake to occur in your region, you can always develop the probable earthquake that is expected to occur in your region. So that a probable ground motion that would be expected in your region in the event of occurrence of earthquake can be developed well in advance. And those accelerations that are developed, what we call, sometimes people use artificial accelerations, but the scientific term is synthetic accelerations then. So these accelerations have to be developed based on based on spectrum compatible time histories, because in IS code, all IS codes and other international standards, they're given for earthquake resistant design of structures, the what are called response spectra curves. And by conforming to the response spectra curves, we have to develop spectrum compatible time history of accelerations. So for that, we used one code that is developed by well-known professor Vinay K. Gupta from IIT Kanpur in 2002, and he is a research scholar Mukherjee and Gupta, they developed during that particular time one program, and we requested them, and we wanted to use that program to develop artificial acceleration, synthetic acceleration, and they were very magnanimous to share that code for us. And at the same time, not only sharing, Professor Vinay Gupta guided us also from India when I was in UK while conducting this developing these compatible time histories then. So we developed a compatible time history of earthquake pertaining to Kolkata coming under zone 3, and the zone factor IS code is 0.16 as per global seismic hazard assessment map. So 0.16 G is around 1.6 meter per second square is the peak ground acceleration at the bedrock. Then we use that code or software, developed spectrum compatible time history of accelerations, and we need what is called a similar earthquake from the record, which will have a close acceleration, so that this is for Kolkata, it is zone factor is 1.16. It is around 1.6 meter per second square or 0.16 G, and we have chosen a seed accelerogram, very close to the target. Very close to the target. Uh, uh, I would like to ask the organizing committee, can you give me some more time so that I can,
5 minutes.
or if you allow me another 15 minutes so that I can, if even participants are also accepting.
Sir. 10 minutes, it is fine, sir.
Okay, fine. I will just quickly, because I have many case studies, I'll just, so that what we did at the end.
11:45 we will
Okay, so fine. Thank you.
do a session and we'll have discussions for 10
Okay,
minutes.
then fine. I'll just quickly close this. Please remove your scrubbings. Remove these things. Yaraj. Rekha?
Sir, we'll look into that, sir.
Okay. So we like that. We developed amplification map very similar to what we developed in for Bhuj place area, particularly Andhra place area. And then we compare the accelerations. Now, peak ground acceleration at the bedrock was 0.16, but by the time they reached the ground surface, the accelerations were 0.2, 0.24. So you can simply divide this 0.24 by 0.16. So you may get around 1.42, and then another site 1.4, 1.64, and there again it is 1.34, and at the site 4, location 4, 1.73. What does it mean? So the accelerations were, if it is 0.16 G at the bedrock, okay, they increased by 42%. Again, 64% and 34%, 73%. So that these are all the likelihood of the acceleration values. So where you can consider for earthquake resistant design of structures. So this is finally we compared our findings with our IS code spectra. Please note that this is our IS code spectra. This is 2002 code, okay, during the time. So this is the rock spectra, and this one type 1, type 2, type 3, type 4, we are not normalized it, and we have simply have taken, okay, and the spectral acceleration we calculated from our analysis 0.947, 0.911, 0.777, 0.943 spectral accelerations. Then we divide that PGA, peak ground acceleration, 0.16. Then it is IS core spectra, and this is a rock spectra. This is soft soil and medium soil, as you all know that. And please know that the values as recommended by IS code 2002 code 1893, that are terminating at 2.5. But here in the Calcutta region, we are noticing this site amplification, and this spectra must have been slightly above that, not 2.5, it's around 2.5, 2.3.8 value then. This is what we observed from our studies, that this is the IS core spectra for rock as well as medium soil and soft soil. But from our analysis, we found that the spectral accelerations are still high. So that what we can conclude from this is that a site-specific ground response studies are very much required to revise our codal spectra, which will enable our structural engineers to go for the proper earthquake-resistant design of structures by adopting such realistic the response spectra curves. And I am having one more presentation, but due to time constraint, okay, I will just stop at this point, and I will just wish to interact with you on some other occasion.